Today, we are diving into one of the most important science books ever written, Stephen Hawking's A Brief History of Time. We're going on a journey to understand humanity's incredible quest for a single theory that explains our entire universe. So, to really get a handle on this cosmic journey we've been on, let's start with a classic story. You might have heard it before. It's often told about the philosopher Bertrand Russell, who was giving a big lecture on astronomy. Now, I know what you're thinking. An infinite stack of turtles? It sounds kind of ridiculous, right? But what this story does so brilliantly is highlight a fundamental problem we've always faced. How do we actually explain the universe itself? What's the foundation for everything? And really, these are the big questions that keep us up at night, aren't they? They're what drive our curiosity. For thousands of years, we've been hunting for answers, and our picture of the universe, well, it's changed a lot. Forget this, over 1,500 years, the Ptolemaic model of an Earth-centered universe was the model. It was super complicated, sure, but it seemed to work. And, it conveniently left a lot of space outside the last sphere for heaven and hell. But then, a much simpler, way more elegant idea started bubbling up and was about to spark a revolution. And what's just wild is how quickly things started to change. I mean, look at this timeline. For centuries, our view was pretty much static. And then, bam, our understanding just exploded. We went from Copernicus' brave but quiet proposal to Galileo pointing his telescope at the sky and proving it, all the way to Newton and his universal laws, which, for a good long while, seemed to explain absolutely everything. So, Newton's theory was a game changer, right? It was incredibly powerful. But there was this one huge, glaring problem that his own laws created, especially if the universe was just sitting there, static, like everyone believed. Yeah, even Newton himself was scratching his head over this one. His best guess was that maybe in an infinitely big universe, the gravitational pull on any star would be equal in every direction. But we know now that kind of setup is super unstable. The slightest nudge and the whole thing should have collapsed in on itself. This puzzle, and others like it, baffled scientists for centuries. And then, 1929 happened, a single year that would completely flip our understanding of the universe on its head, all thanks to an American astronomer named Edwin Hubble. What he found was just mind-blowing. The universe wasn't just sitting there. No, it was expanding. And not only that, but the farther away a galaxy was, the faster it was flying away from us. This one observation completely changed cosmology forever and solves that old paradox of why the universe hadn't collapsed. Okay, so fast forward to the 20th century. This is where things get really interesting because we ended up with these two amazing, incredibly successful theories about how the universe works that just don't get along at all. On one hand, you've got Einstein's masterpiece, general relativity. This is the theory of the epic, the grand scale, planets, stars, galaxies. It tells us that gravity isn't really a force, it's just the shape of space-time being bent and curved by mass and energy. Beautiful stuff. And on the other hand, you have quantum mechanics. This is the weird, wonderful, and frankly bizarre world of the super tiny. Atoms, electrons, all that stuff. It's a world where things can be in multiple places at once and where probability is king. And right here, this is the heart of the problem. It's the central crisis of modern physics. You have one set of rules for the big stuff and a totally different set for the small stuff, and they just fundamentally disagree. They can't both be the final word. This is the great puzzle that physicists like Hawking have dedicated their lives to solving. Okay, so let's circle back for a second. Remember Hubble's expanding universe? Well, that discovery has this absolutely profound implication if you just do one simple thing. Hit the rewind button. Think about it. If everything's moving apart from everything else right now, that means yesterday it was all a little closer together. And if you keep rewinding and rewinding, you eventually get to a moment when everything, the entire universe, was squished together at a single point. And that brings us here, to the Big Bang Singularity, a point of infinite density where space-time is infinitely curved. This is the point where our science, our beautiful theories of general relativity and quantum mechanics just break. They stop working. And it's this idea that brought the question of the universe's origin out of philosophy and squarely into the world of science. This ancient idea from St. Augustine is just perfect for this. It's a real brain twister. You can't ask what came before the Big Bang, because the word before literally has no meaning. Time itself began with the Big Bang. Mind-bending, right? All right, so all of this, the expanding universe, the two warring theories, the singularity, it all leads us here, to the ultimate quest of modern physics. This is the whole point of Hawking's book. So what's the end game? What is the final goal? According to Hawking, it's nothing less than a single, complete, unified theory, a theory that can describe everything in the universe, from the first flicker of the Big Bang to the way we're thinking about it right now. So how do we get there? Well, the idea is to unite the four fundamental forces of nature you see here. We've actually made some amazing progress. We've managed to unify the electromagnetic and the weak forces. But there's one stubborn holdout, the biggest challenge of all, gravity. And that's the holy grail, right there, a quantum theory of gravity. This is the theory of everything we've been talking about, the one theory that could finally patch up that huge fight between the world of the big and the world of the small. And maybe, just maybe, let us understand that very first moment of creation. But you might be asking, why? What's the point? And Hawking's answer is just beautiful. He says it's not about building better gadgets or faster computers. It's about a deep, fundamental human need to understand who we are and where we fit in this vast, incredible cosmos. And that is the incredible question this whole quest leaves us with. If we actually find it, a complete set of laws for a universe that needs nothing outside of itself to exist, what does that say about us? As Hawking put it, we would know the mind of God. And that forces us to ask the biggest questions of all, about meaning and our own existence.
What's your thought about this? Drop your answer in the comment.